Hello, this is Jeff Badger, the Grinding Doc, and this is going to be a video about the different types of abrasive grits. We've got 4 of them, and most people, when they think of grits properties, they think of hardness. Hardness is a big one, that's true, but we're also going to spend some time on chemical reactions, because that's a big deal in the different type of grits. So when I give my classes, I have my 4 grits right here. Whoops. I have my 4 grits, and I name them, I call them aluminum-oxide, silicon-carbide, cubic-boron-nitride, CBN, and diamond. And we're going to go through those one by one, and we'll talk about the hardness. The hardness is easy. Hard, a little bit harder, very hard, super hard. Silicon carbide is slightly harder than aluminum oxide, not much. CBN is pretty damn hard. And of course, diamond is the hardest material there is, okay? But in addition to that, we've also got the chemical reactions going on. So let's take these grits one by one and walk through what they do, when you use them, their hardness, their chemical reactions, stuff like that, okay? So let's start with aluminum oxide, which is what I use this little guy for. And sometimes I use this one if I want to say, oh, it's pink aluminum oxide. In the old days, aluminum oxide, corundum is what it was called, was dug out of the ground. So there is a chunk of corundum. It's still aluminum oxide. It's still Al2O3, but it wasn't made in a factory. It wasn't synthesized from aluminum and oxygen. It was actually dug out of the ground. In the old days, they dug it out of the island of Greece and Naxos, Greece, and various other places, okay? And you can make gemstones out of that. But now we make it. And there's different types: brown, pink, white. There's monocrystalline. There is ceramic microcrystalline. And sometimes they use a different color for that. But that is still just a special type of aluminum oxide. Let's go with aluminum oxide. It's hard. It's pretty damn hard. It's not near as hard as diamond, but it's still one of the hardest materials there is. It's much, much harder than steel. So the fact that this steel is 65 Rockwell, that doesn't mean anything, because this thing is so much harder than the 65 Rockwell steel that it has no problem cutting it. In fact, 65 Rockwell steel or unhardened steel, there's really not that big of a difference in grinding them. Some people would argue with me about that, but in general, the aluminum oxide can cut the iron carbon steel just fine. Now, here's where things get complicated. The aluminum oxide and the steel chemically react. And here's what happens. The iron in the aluminum oxide and the steel forms a thin iron oxide layer immediately. But this guy comes through, and there's a chemical reaction between the aluminum oxide and the iron oxide. It's rather slow. It's not horrific, but it does occur. Now, there's also a chemical reaction that occurs if we grind stainless steel. And stainless steel is the troublesome one. Stainless steel doesn't form an iron oxide reaction or iron oxide layer. It forms a chromium oxide layer. And that chromium oxide layer, Cr2O3 and Al2O3, chemically reacts. And they just dissolve in one another. They stick to each other. Nasty things happen. That's why stainless steels, or anything with a lot of chromium, also your nickel alloys, also your D2s, are nasty to grind. It's not the hardness that makes them difficult. It is the chemical reactions that are occurring. And I talked about that on a different video, so I'm not going to spend too much time on that. But that's aluminum oxide. Now we come to silicon carbide. Now, silicon carbide is only a little bit harder than aluminum oxide, and it really is not that big of a deal, that difference in hardness. Silicon carbide does not exist in nature. You can't dig it out of the ground. You have to make it in a laboratory. And if you make it in a laboratory, you get a big chunk of stuff that looks like that. Nice and pretty and shiny and colorful, and it is silicon carbide. Now, you might say, why don't we grind steel with silicon carbide, because silicon carbide's harder? And you can get away with it. However, silicon carbide has a problem. Silicon carbide has carbon in it, silicon carbide. Iron, steel, and the iron in the steel, because steel is iron plus carbon, iron likes carbon. That's why we stick carbon in steel. So what happens is when this silicon carbide goes to rub against the steel, the iron just sucks up the carbon. and we get a chemical reaction, you can call it. It's dissolving away. It's solid, it's dissoluble. Carbon is soluble in iron. So what we're doing is dissolving it away. Now, you can do it. You can live with it. It's not terrible, but it is an unpleasant chemical reaction that occurs. Now, some people will grind cast iron with silicon carbide over aluminum oxide. Now, cast iron is still a lot of iron. That's why it's called cast iron. But it has so much carbon in it, at least this is the theory. It has so much carbon in it that it's already saturated with carbon that the iron is not going to suck up any more carbon. So therefore, some people like to grind cast iron with silicon carbide because it's a little bit harder and we don't have to deal as much with that chemical reaction. Now, the next one is CBN. I use this. This is obviously not a CBN grit, but I use my little rock here to represent CBN. Now, CBN is nice because it doesn't chemically react with anything. It's pretty much inert, mostly inert. Nothing's really completely inert. So CBN doesn't react with the iron oxide, doesn't react with the chromium oxide. It doesn't start to fall apart until very high temperatures. So diamond will start to fall apart at, let's say, 700 degrees C when it starts to graphitize and oxidize. CBN doesn't really happen until much higher temperatures. So CBN's nice. However, CBN does have one nasty chemical reaction, and that chemical reaction is the CBN will react with steam in the grinding zone. So we're grinding. We grab a grinding wheel here. We're grinding. And we got some water-based coolant going in there. Now, on a very localized level, that water-based coolant is turning to steam because temperatures in the grinding zone are easily getting to 400 or 500 degrees C. It evaporates the steam, but then the steam condenses again. So just for a split second, it goes from water to steam back to water. But when it's in the grinding zone, it turns to steam. And then what happens with the steam is there's this nasty chemical reaction that occurs, and I won't get into it in depth. I'll do that in another video. But what happens is this boron nitride grit forms an oxide layer. That oxide layer dissolves away into steam, and then we're just eroding and eroding and eroding the grit if we grind CBN with water-based coolants. And that's why CBN doesn't like water, number one, and that's why plated CBN is a disaster when it comes to water. So when people are grinding with plated wheels, my first question is, are you using water-based coolant? And if they go yes, I say, ooh, pain is suffering. Or if they're thinking of switching to aluminum oxide, if they're thinking of switching from aluminum oxide to CBN, my first question is, do you have water-based coolants or oil, 100% oil? Not emulsion with oil in it, but 100% neat oil. And if they say, oh, we're grinding with neat oil, I say, okay, then we're good. So as a general rule, the CBN does not behave well with water-based coolants. Now, if you have a bonded CBN wheel, you can probably get away with it because we just dress away our sins. If you have a plated CBN wheel, pain and suffering, you may not even be able to do it because we can't dress away our sins. I talk about that more in depth in a different video. Finally, we have diamond, and I represent diamond with my little rock here. That's obviously not a diamond to be a big diamond, but that's the diamond. Now, diamond is super hard, and that's nice, and that's why we can grind ceramics, we can grind other stuff. We can even grind steel with diamond. It's not pretty, but you can do it. But diamond has a few issues of its own. One of the issues with diamond is carbon. Iron from steel, what is iron like? Carbon. So when the diamond rubs against the steel, what happens? You just dissolve away the diamond because that iron is sucking up the diamond because the diamond has carbon in it. That is an issue for people who are grinding tungsten carbide and steel in the same go because, oh, we grind most of the tungsten carbide, the diamond is a good choice, but then we grind a little bit of steel in the process and it's nasty. Now, we live with it. It's not pretty, but it's not an ideal situation. So that's number one. The diamond is chemically reacting with the iron. Number two is diamond is a crystal. It has a certain crystal structure, and that crystal structure changes as the temperature gets above, let's say, 700 degrees Celsius. So if you put this guy above 700 degrees Celsius, the diamond graphitizes, and it's no longer a diamond. It's just carbon, and it just busts away. So that's problem number one. Problem number 2 is the diamond oxidizes. It just burns. It creates carbon dioxide and contributes to greenhouse emissions. And so what's happening is this guy gets hot, he's oxidizing carbon dioxide, basically just burning away. And as he burns away, he gets a flat, and then we get lots of nasty, unpleasant things happening there. And of course, oxidation occurs more quickly at high temperatures. So that's why with diamond, we got to try to keep the temperature below 700 degrees C. If the temperature gets above 700 degrees C with CBN, boron nitride, we're probably going to be okay. All right, so those are our different grits. That's a little intro, very, very quick, of our different grit types and also the chemical reactions that occur. Aluminum oxide, silicon carbide, CBN, and diamond. And in the old days, silicon carbide was corundum right there. And you got to be aware of the hardness, but you've also got to be aware of the chemical reactions that are occurring. And in my other videos, I talk about how you cope with those chemical reactions. You want to cool well. Sometimes you want to cool well, not to cool well, but you want to cool well to retard those chemical reactions in certain materials, something I talk about in my course a lot more. So that's that. This is Jeff Badger, the Grinding Doc. Quick introduction to grits, quick introduction to hardness, quick introduction to chemical reactions that occur between the grit and the workpiece in grinding. To learn more, get a copy of the 4,000-page book of grinding. To learn more, take my 3-day high-intensity grinding course.